Okay, well, welcome everybody, and it's my great pleasure to welcome you to our 21st Inspiration Exchange session. For those of you who don't know me yet, my name is Fergus Imrie, and I'm a postdoc in the Schaar Lab, and I'll be hosting today's session. Thanks as always to Tennyson Liu for his help in organizing these sessions. So today's topic for the Inspiration Exchange session is frontiers in interpretability. But before going any further, our lab's recruiting for our next year's intake of PhD students. We've got a number of fully funded positions available, so if you're interested, please apply using the form on our website. And so to do this, go to vanderschaar-lab.com, click on the Join Us button, and complete a short form. And this is incredibly important if you're interested in doing this right now, because next Monday, we're going to be holding a recruitment meet and greet session at 3 p.m. UK time. And this will enable you to meet us, have a chat with some of our PhD students, and understand a bit better what a PhD in our lab would entail. So please don't delay in doing that. We'll be sending out some more details very shortly. So back to today's session. As I said, today's session is on frontiers in interpretability. And as an overview of today's session, after my very short introduction, Professor van der Schaar is going to give a brief tutorial and introduction to interpretability for machine learning. After this, two of our PhD students in the lab, Jonathan Crabbé and Alicia Curth, are going to give short presentations describing some recent work in this area. We'll then move to a roundtable discussion where we're delighted to be joined by two guests from industry who I'll introduce more fully later on in today's session. After this, we're going to open the discussion and invite everybody to ask questions of both the presenters from our lab and our industry guests. As usual, if you want to ask a question of anybody in today's session, please post your questions in the Inspiration Exchange channel on Slack, and we'll try and take as many questions as we can. We'll post the Inspiration Exchange Slack link in the chat now, so you can join this channel if you've not done so already. But without any further ado, I want to pass over to Mihaela for a short tutorial on interpretability and for her to welcome everybody. Thank you.
Thank you very much, Fergus, and thank you very much to everyone for joining us. Also, very big thanks to Bien and Jianying for joining us today. I'm going to give a very brief overview, not of the important topic of machine learning interpretability in general, but I'm going to mainly focus on what machine learning interpretability means in medicine, why it is so important to turn black boxes into white boxes. The goals of machine learning for healthcare are well known to everyone that is joining us in Inspiration Exchange, because it is the goal of our community: to deliver precision medicine, to understand bases and trajectories of disease, to empower healthcare professionals, as well as patients, to inform and improve clinical pathways, to transform population health and public health policies, and enable new discoveries. But to do so, we really need to have interpretable and trustworthy machine learning. We need to understand why a prediction is made by the model, as well as what can we learn from the model. And of course, besides these two, interpretability and explainability points, it is also very important to understand how trustworthy is the model's prediction. We need to know what the model knows and what it doesn't know. Today, we are not going to talk about trustworthiness, even though our, as well as our community on machine learning in healthcare, is doing a lot of work in this area, and trustworthiness is equally important to interpretability. But today, as I mentioned, we are going to focus on understanding these models and understanding what the predictions of machine learning models are saying. And of course, the whole topic of interpretation and explainability is multifaceted. Clinicians, for instance, may want to understand why a treatment is recommended for the patient at hand on the basis of a machine learning model. A researcher, for instance, a clinical researcher or biological researcher, may want to understand on the basis of the machine learning models, what are the data-induced hypotheses that this machine learning model is putting forward. And possibly a patient may want to understand recommendations that are made to them, and potentially what is really the most important information that they can act on in order to reduce the risk, or, for instance, when and whether they should give informed consent. We have worked on machine learning interpretability for healthcare over the past 7+ years. And if you go to our research website under research pillars, you will see some of this research and its evolution over the years. We started around 2016 by developing machine learning models that are white box models, that are interpretable by design. And for that, we focused on clinical data, cross-sectional data, and issue risk predictions. In a set of papers from which I'm just highlighting two here, we built an interpretable model, interpretable by design, a method that is called TOPS, which stands for Tree of Predictors. This work, which was developed together with my former PhD student, Jin-Sung Yoon, was then applied to a variety of medical applications, inclusively applications to heart transplantation prediction. And Newsweek featured this work, and they said that the algorithm can predict if you live after a heart transplant with scary accuracy. And indeed, these white box models for static cross-sectional prediction are very powerful, interpretable, and very accurate. But is this the end of the story? We have, over the past several years, worked very closely with clinicians to understand what type of analytics they need to have at their disposal to empower them to better treat their patients. More recently, we developed a sister engagement session to the Inspiration Exchange that is dedicated to discussing with clinicians and aiming to understand the problems that they face and what analytics we can build to empower them. That session is called Revolutionizing Healthcare. And interpretability has been at the core of our discussions, because in order to build actionable analytics, we need to have interpretable machine learning methods. And what we have discovered is that in medicine, we need to go beyond static predictions. It is to build predictions for cross-sectional data. Then methods such as the Tree of Predictors, which are interpretable by design, are white boxes, are in many cases sufficient. But in medicine, we need to do time series prediction when we need to learn from longitudinal data. We need to do clustering and phenotyping and deal with personalized treatment effects, as well as many others. And for this, unfortunately, the performance of the majority of white box models is not sufficient. So we need to rely on black box models. Hence, it becomes extremely important to have interpretable machine learning models and to turn these black boxes into white box models through post hoc explanations. So the lab has developed a large variety of methods for post hoc interpretability of time series predictions, clustering, and more recently, treatment effect estimation. A key challenge for us was to build explanations that are useful for clinicians. What we have discovered around 6 years ago was that what we, the machine learning community, believes is useful for clinicians is not necessarily what they think as being useful. So we have had a series of conversations with them to understand what is really useful for them. If you want to hear more about our discussion with them, you can read on our website a blog that I have written a few years back summarizing these discussions, or my Turing lecture, which was dedicated to this particular discussion with clinicians and what clinicians think it's important when dealing with machine learning in order to find these methods useful in practice, and what white box interpretability and explainability means for them. A brief summary of that is highlighted here. We need machine learning models that provide explanatory instances in terms of features, but also in terms of examples. We also need, as we are going to discuss more today, to discover concepts of interest, especially when we look at longitudinal trajectories of disease. We also need personalized explanations, and here by personalization, I do not mean personalization to the patient and the input, but rather explanations that are personalized to the user of the machine learning model. Finally, many clinical regulatory bodies, such as the Joint Committee on Cancer and many others, need explicit formula, methods that are as transparent as regressions, but possibly nonlinear. The lab has developed methods for all of that over the last years, and the agenda is continuing. Today, Jonathan will talk about interpretability by discovering concepts, and Alicia will talk about the work with Jonathan and Ioana on interpretability of individualized treatment effect estimation methods. If you want to read more about the work we are doing on interpretable machine learning with a focus on healthcare, once again, take a look at our website. And maybe even more importantly, we have built together a set of resources in our GitHub where we collected all the different interpretability methods that the lab has built over the last years, as well as some of the main methods developed by others. So please take a look and engage with these resources. Thank you.
Thank you, Mihaela. Next up, I'd like to invite Jonathan Crabbé, one of our PhD students, who's going to give a presentation on concept activation regions. And if you have any questions for Jonathan, please post them in the Slack channel. And as always, the earlier is better to post these questions.
Amazing. Okay. Well, thank you very much. Very happy to be here with you today. So I'm going to talk about this very, very interesting subject that is concept-based explanations. Of course, I'm only going to cover the tip of the iceberg. I mean, as Mihaela has said, like we have done a lot of work on interpretability. Concept activation and concept explanations is only part of the story, but we have done a lot on feature importance, example-based explanations, and even interpretability of unsupervised models. So if you want to learn more about this, again, there are some resources online, and you can follow this link here. Of course, I'm not the first one to talk about concept-based explanations. I actually did not invent this, like Bin Kim, which is on this call, did this. So if you want to learn more about these foundations, the foundation work on this subject, please follow one of these two articles here. So without further ado, let us talk about concept-based explanations. Maybe let's start with a couple of definitions. What do we mean by concept? I think that's already a good start. In this case, actually, it's very simple. Like concepts are just defined by the users by providing concept positive and concept negative examples. What do I mean by that? Maybe let's consider an example. Imagine you want to define the stripe concept and you have an image classifier. Well, you can simply just give a lot of examples that have stripes, you know, those we call the concept positive examples, and examples that don't have stripes, those you call the concept negative examples. So in this way, you have examples with and without the concepts. So in this sense, you can kind of consider this concept as a binary human annotation that is present on each of the examples you feed to your machine learning models. Of course, this annotation needs to be deducible from the features you're observing. So it doesn't really make sense to talk about a sound concept if all you have access to is image data, for instance. Okay, so now let's talk about concept explanations. What do we mean by that? Well, simply you have a neural network. In a typical setting, you have a neural network that does classification. So in this case, you know, like the neural network recognizes there is a zebra on this picture. So I'm a human, I can also recognize a zebra on this picture, but I will actually resort to high-level concept in order to do that. For instance, I see that the zebra has stripes. That's an important concept for me to identify a zebra. So I can actually ask the question, is the model actually doing the same thing? Is the model paying attention to this kind of stripe concept in order to identify that there is a zebra on this picture? Of course, this is not only limited to the realm of image data. You can also do that with medical models. So for instance, if you have, you know, prostate cancer patients and their data, you can predict their mortality with a neural network. And again, as a doctor, maybe you might want to interrogate this neural network and ask questions like, we have grading system as doctors, or actually doctors have grading system. Is the model using actually this grading system? Is the concept kind of, each of these grade can be seen as a concept, like, are these concepts important for this neural network to reach, a prediction for the patient? We're going to go back on this example a bit later in the talk. So the way people do concept explanations is usually by using the concept activation vector formalism, which I'm going to detail now. It's actually a very simple formalism if you think about this. You have concept positive and concept negative examples. So this is what you start with, but you also have a model that you want to explain. So what you're going to do is you're actually going to probe the representation space of this model. So in this case, I'm just going to take a cut at the penultimate layer of the neural network, for instance, and kind of look what's happening in this representation space. So I'm going to map the concept positive and negative example in this representation space and see how they are distributed. So I'm going to zoom on this representation space now so that we see a bit more clearly what's happening. So as you can see here, the concept positive examples are grouped together and the concept negative examples are grouped together. And in particular, they are linearly separable. So I can just have a hyperplane that kind of cuts and separates the two families. So now that you have this hyperplane, you can actually have vector that points normally to this hyperplane. This is what people call concept activation vector. And you can kind of convince yourself of why it is called like this intuitively. It's actually pointing in a direction where the concept positive examples are grouped in this representation space. So of course, now that you have this direction in the latent space that encodes this concept, you can compare it to other directions. So for instance, I could compare it to the direction where the probability of predicting a zebra increases. And I can see here that these two vectors are kind of pointing in the same direction, which indicates that the model kind of relates the stripe concept to the probability of predicting a zebra. So the zebra class is related to the stripe concept in this case. So all of this is nice, but I've actually made a big assumption here. I've actually assumed that concept positive and concept negative examples are linearly separable. What if I have something like this, in which concept positive examples are still grouped together, but they are not linearly separable from concept negative examples? Well, in this case, if I want to make concept-based explanations, I need a generalization of this concept activation vector formalism. This is the concept activation region formalism that we introduced in our NeurEPS paper. So the idea is actually simple. You can just cut this representation space in two parts. One part that we call the concept activation region that has the concept positive examples, and the complementary region in the representation space. In order to formalize this, we actually borrow the smoothness assumption from semi-supervised learning. The idea is that we say that the concept is well encoded in the model representation space if this representation space is smooth with respect to the concept label. So I'm not going to detail like this definition here, but intuitively, this means that I can kind of split the representation space in two regions. One that is the concept activation region that mostly overlap with concept positive examples. One that is the complementary region that actually overlaps mostly with negative examples. And I need these two regions to be well separated from each other in terms of clusterability. You can convince yourself that concept smoothness actually generalizes linear separability, in that linear separability is just a particular case of concept smoothness, but you can have concept smoothness without having linear separability of the concept sets. What's good also with this semi-supervised approach, it actually provides us a very nice way to define this concept activation region. And we do that by actually using kernels. So you can kind of define kernel densities by assigning positive densities to the concept positive points and negative density to the concept negative examples. And once you have done that, you can deduce the concept activation region by using a sparse machine. So I'm not going to detail that because of time, but if you want these details, of course, everything is in the paper. Now that you have this concept activation region in latent space, you can see how these concepts are related to classes by seeing how many examples of each class falls in one concept activation region. This is how we define the overlap between classes and concepts. Also, we define feature importance scores for each concept by using this concept density here. And it actually tells you how important is each feature in order to identify the presence of a concept. Okay, so now you might ask yourself, okay, this is a very heavy formalism. Why would you actually need this? Is it very important to kind of have nonlinear separability between the concept activation regions? Well, the answer to that is yes. As we show in the paper, this leads to a much more precise way to characterize how concepts are distributed in the representation space of deep neural network. Furthermore, it leads to explanations that are in better agreement with human annotations, so human ground truth, if you want. And finally, it leads to feature importance that is that reflects well the associations between concepts. So concepts that can be identified with the same features are actually reflected. This is reflected in the feature importance scores specific to each of the concepts. So I'd like to finish by just presenting you an application of this concept activation region formalism. I think it can actually be very useful in the scientific assessment of machine learning models. So the use case we consider in the paper is the prostate cancer grading system. So what we do is basically we train a deep learning model to predict the mortality of prostate cancer patients. And then we interrogate this mortality risk model with grades that are familiar to doctors. So we use here the grading system that doctors use in order to assess the likelihood of prostate cancer spreading. So the higher the grade, the higher the probability that this prostate cancer is going to spread. On each of these grades, you can consider it as a concept. I know you might ask yourself, is this concept very well encoded in the model representation space? And by using concept activation region, we were able to show that yes, with very high accuracy, representation space makes a separation between patients with different grades. And furthermore, in this representation space, higher grade is associated with higher mortality predicted, higher predicted mortality. So this is consistent, of course, with the definition that the doctors are using. Of course, this is only an example, but I just want to show here that these concept-based explanations might be very useful to kind of validate machine learning models just beyond, simply measuring like 2 metrics on a test set. I think it's a very interesting complement to this kind of validation approach for machine learning models. So there are a lot of things I was not able to cover in this talk, but that are in the paper if you are interested. So of course, I invite you to read the paper if you want to learn more about this. And there are a lot of resources in our lab if you want to go beyond this talk in explainability. So I really hope you enjoyed the talk, and I thank you for your attention.
Next up, we have Alicia Curth, who is going to be talking about interpretability in the context of treatment effect estimation.
Hi, everyone. My name is Alicia. I am also a PhD student with Mihaela. And I will be talking today about our paper, Benchmarking Heterogeneous Treatment Effect Models Through the Lens of Interpretability, which is joint work with Jonathan and Joanna, who's just graduated our lab. And to give a little bit of background, so I normally work on treatment effect estimation, whereas Jonathan normally works on interpretability. And here we've kind of put the two topics together and looked at interpretability not as an end goal, but as a way to benchmark the quality of treatment effect models. So we are interested in interpreting machine learning methods for estimating individualized treatment effects in this paper. That's because estimating personalized effects of treatments is a very complex problem that's important in many fields, and especially in healthcare, if you want to give good personalized treatment recommendations, for example. The machine learning literature has recently proposed many sophisticated but opaque treatment effect estimators, which usually propose some kind of black box machine learning algorithm that output a number representing the estimated personalized effect. Usually, and in all papers that we're aware of, these have mainly been evaluated in terms of getting the numbers right. So in checking how close the estimated function is to the underlying effect function. In our paper, we argue that this may not be enough, and that instead we may want to evaluate not only the numbers that are being output and how close they are to the truth, but also whether we have actually learned something real. That's because we'd often like to derive some actionable insights from these individualized treatment effects estimation models. So for example, we might want to perform some kind of scientific discovery and look at what the drivers of effect heterogeneity are that we've actually learned about. This could be useful to find groups that have some kind of enhanced treatment effect, or this could be used to do the opposite, to find groups that for which a treatment doesn't work or even causes harm, so that they can be excluded from future trials or prescription criteria, if we're looking at a clinical trial of a drug, for example. Because this is our goal, we ask a key question in this paper, namely whether existing individualized treatment effect estimation strategies discover the true drivers of effect heterogeneity. To do so, we first investigate how to use feature importance methods in the first place to interpret black box ITE estimators, and then use this to evaluate them on a new task, their ability to discover the drivers of heterogeneity. To do so, we propose a new benchmarking environment and then provide a set of experiments that hopefully gives new insights into existing ITE methods. We consider a standard setup within this potential outcomes framework. We assume that each individual is characterized by some covariates X and an outcome under treatment and a potential outcome without treatment. We're interested in estimating the conditional average treatment effect, or CATE, which is the expected value of the ITE, and is the difference, simply the difference between someone's outcome under treatment and without treatment. In this paper, we were interested in how would we interpret such an black box estimator. And here we, by interpreting, we're simply looking at what covariates does the machine learning model that we're outputting pay attention to. We argue that interpreting treatment effect models is different from interpretability or from looking at feature importance in a standard supervised learning context. And that's because instead of just one type of important covariates, there's actually two types of important covariates in this problem. On the one hand, we have something that we call prognostic covariates, and these influence outcome regardless of treatment. So they actually affect both potential outcomes. And these could be common risk factors that are always important, for example, age. On the other hand, there's something called predictive covariates, which determine differential responses to treatment. And these are the true drivers of heterogeneity, for example, hormone receptor status in cancer applications, which affect the potential outcomes differently. And we argue that it's really only of interest to look at discovery of these predictive covariates in treatment effect estimation applications, because these are the ones that matter when interpreting the learned effect function. Unfortunately, many black box CATE estimation strategies do not have built-in measures to show which features are being paid attention to. And therefore, our approach is a simple one where we simply propose to use off-the-shelf feature importance methods that output some kind of attribution score when looking at the estimated effect function to assess whether an ITE estimator has learned that a specific feature is predictive. Here, the importance increases with the absolute value of the importance scores. And to actually implement this, we could use any kind of existing feature importance method. We want to use this this way of interpreting what models have learned to evaluate different estimators on the question whether they have paid attention to the correct covariates when issuing estimation. To do so, we define two new metrics to evaluate the treatment effect estimators on. We define a metric we call predictive attribution, which measures the proportion of importance correctly attributed to the predictive covariates. And we define a metric called prognostic attribution, which is the proportion of importance incorrectly attributed to prognostic covariates. And a good model should have the first one be high and the second one be low. To evaluate this, we can unfortunately not use real data because real observational data neither has information on true treatment effects nor on a true covariate classification. Therefore, we propose a semi-synthetic benchmarking environment in our paper, which uses real covariates, but simulates the outcomes and treatment assignments, which ensures that covariate classifications and treatment effects are known by design. We implement a very flexible data generating process in this benchmark. And by varying different factors, or so-called experimental knobs, in these data generating processes, we are able to probe how different models perform under different scenarios. We perform many different experiments in our paper, but here I'm just going to show one where we evaluate different types of black box estimators for treatment effects as we vary one part of the DGP, which we call predictive strength. And this measures how strong the predictive effects are relative to the prognostic effects. Here we plot on the x-axis, we plot the predictive effects being getting stronger. And on the y-axis, we have the predictive attribution. And we see that across all scenarios that we consider, all models get better at identifying predictive covariates as the predictive strength increases. At the same time, when we look at prognostic misattributions, we observe that these prognostic misattributions indeed stop as the predictive effects become stronger. We also compare this to simply looking at whether the numbers are right, the effect predictions are right. And here we see that actually the ordering between the different estimators can change. And it's not the same when we look at attribution scores versus when we look at simply prediction performance. So from this one experiment, we kind of conclude that the strength of predictive effects indeed matters, and that some learners seem to systematically do worse than others, but that using attribution metrics can lead to interesting new insights relative to considering only the standard RMSE metrics. We also, in our paper, investigate the effects of degrees of nonlinearity and the type of degree of confounding, so treatment selection bias. From our experiments, we conclude that benchmarking Kate estimators along a new dimension, namely whether they discover the correct drivers of heterogeneity, definitely brings interesting new insights. And it could definitely be interesting to investigate even more learning strategies and different base methods. An important next step would definitely be to consider whether we can design methods that perform better on this new metric by taking our findings into account. And finally, whether there are other neglected dimensions such estimators should be benchmarked on in the future. This was only as small, as Jonathan was saying, this was only the tip of the iceberg in terms of our treatment effect estimation work. So if you're interested in all things treatment effect estimation, we also have a research pillar on our website. Thank you so much for your attention.
I would now like to move us to our panel discussion, where we're joined by two fantastic guests from industry. Firstly, we're joined by Dr. Bean Kim, who is a staff research scientist at Google Brain, and who you've already heard a little bit about earlier about her work in Jonathan's presentation. We're also joined by Dr. Jianying Hu, who is an IBM fellow and global science leader in AI for healthcare at IBM, and the director of the Healthcare and Life Sciences Research Division at IBM. Today's discussion is going to be chaired by Mihaela, and if you have any questions for our panelists or any of the speakers today, please do post them in the Slack chat. And after several questions from Mihaela, we're going to open up the discussion to participants as well. So without any further ado, Mihaela, I'd like to pass over to you for the first question of our panelists.
Thank you, Fergus. Maybe we can go to the next slide. Wonderful. So Bean, this question is for you. Thank you so much for joining us today. And the question is, do you believe that new classes or types of explainable AI are necessary still? And if so, what do they need to capture that is currently missed by existing methods? And how do you envision future interactions between humans and machines?
Yeah, thanks for that question, and thanks for having me. It's awesome to hear all this great work going in your lab and participate. Just a note of apology in advance. I am very sick right now after traveling last week. So what I say might make less sense than usual, or I would like to think so. So just like fill in the gap for me. If something doesn't make sense, ask follow-up questions. It's all good. Yeah, so the first question, do we need new class or types of explainable AI? So I think it depends, but mostly I've often come to think that we don't actually need more method. We've been making a lot of tools last many, many years, and we kind of have a lot of tools that we yet to have a manual for. How do we use this tool? That's like the biggest question that we need more understanding of. And I love the two talks that just I had honor to listen in just now, like Jonathan's work, polishing the existing method to a better degree and improving. That's fantastic. That's exactly kind of what we need rather than trying to reinvent wheels every time. Alicia's work trying to get at, okay, well, existing methods, can we actually extract those ideas, and working closely with clinicians in both cases, and also Mihaela's talk and working side by side with clinicians. That's exactly what we need. We have these methods. What are the end goals that actually help these methods can help? And that's exactly what we're missing. That's exactly where we should be putting a lot of focus on. Another side of that, another spectrum in that is to improve our fundamental understanding of neural network. What do I mean? Well, in the history of science and engineering, we always kind of did both. We have a very fundamental basic science, physics, chemistry, you name it, even philosophy at times. And we had engineering effort. We build things, we break things, and kind of figure out how things work. These two things are side by side. We have to do it together, and these two will synergize each other. Knowing something about science will encourage making better tools, and vice versa. Empirical results inform science. So we have done a lot of engineering work, in my view. We made a lot of tools, but now it's time to put a little more effort into science. So I've done some work about this kind of what seemingly kind of useless question, like, does neural network has Gestalt phenomenon? Well, who cares? Well, it kind of matters in a very fundamental level to trying to improve our understanding of this organism called neural network. So those are the things that I'm excited about in terms of next steps of XAI. Also, please tell me to shut up if I'm going too long, because I just realized I've just been rambling. Okay, so next question. How do we envision future interactions between human and machine? This is something that I talked about in my ITErpretability keynote. I'm really passionate about this, and I strongly believe actually this is how things will happen. So I believe that we're going to develop a language between humans and machines. What does it look like? I don't mean this to be like natural language processing that machines talk in human language and human talks back. That's not what I meant. What I meant is a brand new way of us communicating. Think about math. Math is a language that we can communicate very complex meaning very efficiently. That's something you taught in school because it's useful in your life. So why not develop a language that would enable us to communicate with machines in that efficient manner? It will not be perfect, as precise as math, but it will be useful, it will deliver meanings, and it will most importantly necessarily require stretch from human side. So we are good at learning new things. We will stretch as we learn this new language and learn new things from machines so that the true synergy between human and machine will happen. And I strongly believe that this will be the direction we're already getting to, that towards that direction in some modular level, and we'll see more rich class of language as we move forward.
Thank you so much, Bea, and I completely share your vision. And the lab has tried to build one type of such language. I hope that there will be many languages for humans and machines to communicate. Our language is a little bit pompously called quantitative epistemology, where we try to understand how humans think and bring them into mathematics that the machines can understand, and vice versa. So maybe subject to a subsequent conversation, but so completely agreed. And I'm really very happy that Jianying could be with us as well, because Jianying and I have been for quite a long time on this journey of trying to make machine learning for healthcare a reality. And I joined this passion for many years and been in discussions for many years to make it happen. So Jianying, a question for you. What, if any, recent developments in interpretability and excite you the most, and especially with respect to machine learning for healthcare?
Thank you, Mihaela. First of all, thank you so much for inviting me here. It's really fantastic to be here. Really enjoyed the talks and also enjoyed the conversation you just had with Bea. Really great ideas coming out of this. So there are a lot of new exciting developments in explainable AI, and the two talks that I just listened to today were really very interesting, different ideas of, to Bea's point, of making sense out of the models and trying to learn more from it. But perhaps I'll bring up another example that's not touched on here. It's somewhat related to what Bea was talking about in terms of combining AI with science, right? So this notion of hybrid AI and mechanistic models is one area that I feel is very exciting in terms of bringing really useful explainability to the models. So what I refer to as mechanistic models are models such as, models for the tissues of the heart or for neural tissues, neural networks that are designed, by design explainable, because it really gets to the actual biological or physiological mechanisms of disease or intervention, the impact of interventions on the human system, etc. Right? So such models have many, many uses. For example, it could be a powerful tool for de-risking drug candidates in preclinical stages of drug development by doing simulations for pharmacokinetic or pharmacodynamic analysis and dosing analysis, right? But on the other hand, these models are very complex, and the parameters of these models are notoriously difficult to infer, particularly when you want to try to actually make sure the output of the model actually, matches what you observe in biological or clinical settings. So this is where, machine learning could come in to help. So in some recent work, there are, AI generative models, specifically in some instances, GANs, that were used to actually solve that inverse problem of inferring model parameters from the experimental observations. A paper that was recently published in the Journal of Pharmacokinetics and Pharmacodynamics showed that using this approach, you can run simulations to get to the parameter space and run simulations to help probe and understand the mechanisms of action for drug in early trial. So, this type of models can be applied in many different areas, and I really feel this combination of the strength of mechanistic models, or what we traditionally do in scientific discovery, with the power of AI methods is one area that could bring a lot of great opportunities in driving new scientific discoveries.
I didn't coordinate with you, Jianying, so this was your answer, but and I'm delighted you think so, because I have a few students in the lab, Christophe and Zhaoji, that have developed a set of methods such as decode, decipher, that do just that. So I'm delighted that you think that this is important. I share your view as well. There are many methods for explainability. What do you think is the right way to use them? Bin has touched a little bit on that, but I want to push both of you a little bit further. And do you believe that there is a wrong way to use them as well? Don't know. And again, maybe focusing on healthcare if possible, but generally it's useful to hear your thoughts.
Yeah, I can give it a go. I will focus on healthcare because that's an area that Mihaela, as you mentioned, that I've been focusing on. I think really you have captured it really well in your introduction. I think the right way to use explainability is to make sure that it's user-centric and that it's context aware. So you gave a lot of examples of the different users of the explanation. Perhaps another example that I can give is in the healthcare domain. When you think about global explainability versus local explainability, you can think of, for clinical researchers, medical profession, professional societies, as well as regulators, the global explanations are what's important to them because they need to learn from the models what it informs them in terms of best practices, medical guidelines, and maybe care management plans, right? On the other hand, when it comes to clinicians and patients, it's the local explanation that they care about. They want to know, why does this model predict that I'm going to develop, let's say, heart failure in 6 months? And how confident is this prediction? What are some of the talks alluded to, what are the actionable factors? So it's really these local explanations that's important, right? So then a corollary of that is, I think, really the wrong way to use explanations is really to attempt one size fits all, to try to come up with one explanation for all the contexts and all the users.
Thank you.
Yeah, completely agree. If there's anything that you all want to take away from this lecture, in addition to what Mihaela's talk, I would say one thing. This one thing, please remember. Bad explanation is much worse than no explanations at all. Bad explanations, just much worse. than not having done it at all. So it's kind of my nightmare, ongoing nightmare, I should say, that what I'm doing my entire life and contributing my intellectual energy, that creates just worse society than I had done nothing at all and drinking martini every day. And we should really take this to our heart, that there's so many wrong ways to use it. It's so easy to use it in a wrong way. There's a striking contrast in literature where there's tons of work, including a lot of my work, that shows, well, these methods don't work. The random network and trained network show you the same explanation. What's going on? Versus in practice and applications, people just kind of use it. People are like, oh, this is cool. Let's throw it and like see what gets out and cherry pick our answers and present to the board because that supports my case, for example. That striking contrast should really alert us. There's something, it's not really working as intended, and work like what your lab is doing, working closely with clinicians to try to get at what is this gap, what's going on, what works and what actually doesn't work is so important. Like to hit this point home, Alicia's talk ended with this sponsor, AstraZeneca is one of your sponsors I saw. And I was thinking, oh, you know what? My parents got vaccines from AstraZeneca. Everything that we do loops back to us. Whatever we do really comes back to our lives and our individual personal life and influences us and influences everybody. So we have a huge responsibility, if not more responsible than the people who develop those models. We're as responsible in interpreting them.
Being this is such a great point, because sorry, Jane, just yes, to echo a point, I think that one of the very important uses of interpretability that we see in our lab recently is debugging models. So we use these methods with clinicians to debug some of the models, and we discuss some of our own models at times. And we discover all sorts of errors and problems and try to really bring this loop together. So model debugging seems to be equally important as model interpretability. And it seems that part of what you said is part of that agenda. Sorry, Jianying.
No worries. So that's exactly, I was going to make a similar point, Mihaela, is to bring up that the importance of building explainable, finding explanations for models. It's important not just because it allows better use of the model and more proper use of the model, right? That's obviously one aspect. But another really important aspect is the drive to have better explainability, and all the probing that goes along with it is actually what's really necessary to build models that are truly useful, that actually address the most meaningful questions and filling the most critical gaps in our knowledge, right? So I think in that way, explainability is actually really, really inherent in the ability to build good models. It's not an add-on, it's not an afterthought, it's actually a requirement.
I like also beans. Let's drink martini instead. I would propose let's eat chocolate instead. Sorry, everybody with their own addiction. Fergus, let's go to the fourth question. And this is my final question from my side. Do you think that there is a trade-off between explainability to understand models and explainability to improve human understanding and knowledge? And will distinct methods be needed for these two goals? Which relates to what we just discussed. So
yeah, I was going to say, Mihaela, I think I just answered that question.
Yeah, I think that this question was not anticipating already the discussion.
Right. Yeah, I think both are important, and I think they feed into each other.
Yeah, agreed. I was going to give a concrete example of one method that we're developing that trying to do this, and I think it's one of the evidence why these are different. So we are trying to study AlphaZero, which is a self-trained chess playing machine, and it was trained by playing against itself and never ever seen human chess play ever. Now, we've done our previous work, how to probe this network and see does human chess concept exist? And the answer was, to the best of our knowledge, like it kind of does. And now we hired a former champion, chess champion, who also happens to be a machine learning PhD student at Oxford, Lisa Schutt. She's my student researcher, which is like a name for intern at Google, working with us to try to learn new chess concept. And our goal is to teach Kramnik, who is grandmaster for 7 years, to see whether he can figure out and tease out some of the new chess strategy that he has never seen before. And we're actually taking dramatically different approach, because the thing is, if we were to be so complex and brilliant in words of noting enough for Kramnik to know this chess concept that we're going to discover, then it's going to take a long time for them to look at it, inspect, and learn. And that's not typically what typical interpretability methods aim to. They aim to efficiently understand, and speed is matter. But in this case, we actually don't care about speed at all. We care about the complexity and worthy of noting concepts. So we're taking quite different approach, which one of the evidence to this question. And we're having a lot of fun. This is such a fun project.
Wonderful. Thank you so much, Bin and Jianying, for all the wisdom and all the insights. Thank you so much for being with us. And I hope you feel better soon, Bin.
Thanks, Mihaela, and thanks, Bin, and thanks, Jianying. If you're able to stay around, there might be a couple of questions for you coming up from the audience, because we are now moving to the more general Q&A session. And so we've had a lot of questions in the Slack, so I will try and select a few of these for our speakers. So if we select your question, I'm going to ask you to unmute yourself, and then if you can very succinctly ask your question, and then we'll get an answer, and we'll try and get through as many as we can. Any we don't get through, we'll try and answer in the Slack channel, so you have a record and we're able to answer your question. So I think the first question we want to take is from Megha for Jonathan about concepts. Do you want to unmute yourself and ask your question?
Yes, thanks. Thanks, Jonathan, for the nice talk. So I would like to ask whether the concepts that you were talking about, are they always predefined, or is there a way to also learn them? Because if they are always predefined, how can you be sure that model always chooses one of those concepts to make its decision?
Thanks for the question. So in my work, concepts are predefined and given by the user. So it's like just a way to probe the model. So it's like, I have my concept positive and my concept negative. I'm just going to probe the model with this.
Yes.
There are some works about concept discovery by kind of analyzing this latent representation of models. Actually, there is a work by Bin that I'm aware of, like where they kind of use image segmentation and kind of discover concept in the form of image segmentation. So if you're interested in going beyond what I'm doing in my paper, I can refer to this paper in the Slack channel.
Okay, thank you.
You're welcome.
I would also
Thanks,
bring up,
Jonathan.
if I may, this notion of, I think it's related to what you are asking, this notion of causal representation learning, which is, this idea of looking at multiple modalities that is related to a particular, type of disease or condition, or let's say heart. And then the idea is learning a joint latent space from these different modalities with the hope of being able to then overcome the issues and bias and noise from each individual modality and getting to a more intrinsic representation space. And so that's a completely unsupervised method. The idea is then these, in many ways, the representation you learn in the latent space are concepts. So it's very much related to this concept learning technique that Jonathan presented.
And then are you able to take back your concepts to human understandable concepts? So because you learned your concepts in...
Yeah, that's to Bin's point, that requires then human machine interaction, right? To be able to interpret that. It's really an interactive process of getting to the latent representation that both supports downstream tasks well, at the same time also have meaningful interpretations.
Yeah, okay. Thank you.
Fantastic. So the next question we're going to take is from Ortal for, I think, Jonathan as well. about using concepts to maybe improve models. Ortel, do you want to ask your question? Maybe they are not here anymore. In which case, I'm going to move to the next question.
Maybe Fergus, you can ask the question yourself.
I see in the chat he's not able to unmute right now. So the question is there a way of using human-defined concepts, for example, the cancer grading score, to kind of force models to learn new concepts from data? And not exactly for interpretability purposes necessarily, but a way of almost doing the opposite. I don't know, Jonathan, if you want to take this, or if Bean, you want to comment as well, perhaps.
I can quickly say something about this. So, I mean, the most obvious thing you could do in this case would just to kind of put this concept as a feature in input to the model and kind of let the model decide if it wants to use it or not. If you want to force the model reasoning in terms of this concept, there are also some works on this, like that are like concept embeddings or concept, like in which like the concept is kind of in the middle, like you kind of detect a concept and then make a prediction. There are also some works like this. I'm also going to refer to that in the Slack. So yeah, but there are some works that kind of force models to reason in terms of concepts that you have pre-specified. Yeah.
Yeah, I guess I will refer to this paper that I think Jonathan and many others we embed those concepts in the bottleneck so that you can control, and clinicians can say, hey, I don't want this feature to be counted for final prediction, and let's change that. Something that weird we did, it kind of worked also, is that you can actually use this concept vectors as a way to label data. So you have this direction in the embedding space, and you can use as a filter to see, oh, there are more concepts like stripes here and less more concepts like dotted here, and it actually did work more surprisingly than we anticipated. It's not published though. I think it's internally done.
Thank you both. I think we've got maybe a slightly related question, but maybe more general from Thea about something. I think she's referring to almost reverse explanations. Thea, do you want to unmute yourself and ask your question?
Yes, sure. I just realized now that it was pretty similar to what was already asked. But yeah, this is more of an idea of like, if there's some way to develop some kind of interactive framework with the models where we can deliver explanations to them that we can sort of regularize the models towards. But I guess this is similar to what Jonathan just talked about. But yeah, these are just some thoughts that I've had with if there's some kind of way to give these models an informative inductive bias that's not just initializing the model somewhere where we think it's relevant, but sort of, yeah. I hope that makes sense.
Maybe I can say something about, so yeah, like definitely there is this work on concept bottleneck models that kind of, but it's like an inductive bias in which you kind of impose the model to think in terms of a pre-specified set of concepts. There is also this, I read a very interesting paper recently, like about saliency maps, in which, for instance, you have some prior knowledge on what the model should pay attention to, or what the model should not pay attention to. For instance, there shouldn't be an overlap between this class and this class saliency map, that kind of stuff. And you can actually encode that in a regularizer and kind of regularize the model on this basis. So yeah, definitely there are some works. I think it's kind of a field in development that I haven't seen a lot of papers on this, but it's kind of feeding in like what Mihaela was referring to earlier, which is like kind of debugging model or improving model by kind of injecting some prior on the type of explanations you might want to receive. Yeah.
Thank you.
Fantastic. I think we've got time for one more question. So I'm going to ask a question of Alicia. I think there's an interesting question from Megha. I know you've asked a question already, but I think this one's quite interesting about Alicia's work.
Hi, Alicia. Thanks for your nice talk. So I was just wondering, how did you trust the explainers, right? So your explainers might be giving you different explanations for the same model and for the same decision. And how did it affect your discovery of related to prognosis, predictors in prognosis or diagnosis?
Yeah, so we thank you for the question. We actually repeated the experiments with 5 different explainability methods. And so in the main paper, we only considered integrated gradients, but we replicated our experiments in the appendix, also with SHAP and feature ablation and feature permutation. And we, across almost all data sets and almost all methods, the conclusions were actually pretty similar. There's just some, I think, feature permutation performed pretty badly on one data set. But apart from that, actually the conclusions from the experiments were almost the same across the different explainers. And then there's in our appendix of this paper, there's actually I think a very interesting discussion of the properties that different types of methods have. The different types of explanation methods have, such as sensitivity, completeness, linearity, and how this relates to desirable proproperties in the treatment effect estimation setting. So if you're interested in that, we discussed that somewhere in the appendix on how a method that's complete, what that says basically about its performance within treatment effect estimation.
I see. But overall, you were able to trust the explainers. You did not get completely different explanations.
No, exactly. We got very similar explanations, quality of explanations across the different explainers in the specific setting that we used here.
Okay.
I also want to commend Alicia in this work with Jonathan and Ioana, because Alicia came up with a very interesting way to semi-synthetically benchmark these methods. And this is, I want to point out, as far as I know, the first framework to enable interpretability, almost like a benchmark for the treatment effect models to be interpreted. And I think we need more of that, as being rightly said, and I want to echo her point. We just don't need more methods necessarily. We may need methods for certain scenarios where we don't have explainers, like Jonathan's work on time series, which still remains one of the few works that explains time series. The same thing here is the first work to try to explain treatment effect estimation methods. But what's interesting in the work of Alicia and Jonathan and Ioana is that we also have a first benchmark. So we invite others to come to this benchmark and try their own explainability, because that may be better methods than the ones we have investigated. Because the focus was not to find the best explainers, but to see what these different explainers do in this benchmark. Thank you.
Thank you.
Thank you, everyone. I think this is all the time we've got for questions. We've already run over a little bit. So any other questions that we've not taken, I'm going to ask Jonathan and Alicia to try and answer as many as they can of the questions on Slack and provide some more detail for everybody. So just before we wrap up, I want to highlight once again that our lab is still recruiting for PhD positions, and also highlight the meet and greet next week. If you're interested in joining and you don't have details for that, please do get in touch with someone from the lab. Finally, just to wrap up, our next Inspiration Exchange will take place in around a month's time, where we will be introducing our new state-of-the-art AutoML platform for prognostic and diagnostic modeling in healthcare, Autoprognosis 2.0. And if you're interested in learning more about this before the session, please visit our dedicated webpage shown on the slide here to find out more. Finally, I just want to say a huge thank you to everyone who's joined our session, all of our speakers, from Mihaela, Jonathan, Alicia, and in particular, both Bean, who is here despite feeling very unwell, and Jianying. So thank you very much for all of the speakers and panelists for joining us. And I look forward to seeing you all at the next session. And thank you very much, and enjoy the rest of your days. Goodbye, everyone.